All right, today we're diving deep, right into the heart of the atom. We're going to try and understand the incredible power that's locked inside, a power that's described by probably the most famous equation in all of history.
Yeah, you know the one. You've seen it absolutely everywhere, right? On t-shirts, in movies. It's become this universal symbol for genius. But what's really hiding behind these 5 simple characters is a truth about our universe so profound it literally changed the course of human history forever.
So, what is it really telling us? Let's forget about the complex math for just a second. At its heart, this equation is a statement, a huge one, about the fundamental nature of reality itself. So let's break it down.
Okay, so here's the really mind-bending idea at the core of all of this. Mass, it isn't just stuff. It's an unbelievably concentrated form of energy. A great way to think about it is like matter is frozen energy. And if you could just figure out how to unfreeze it, well, you'd unlock an incredible amount of power. And that is the key to everything we're talking about today.
So if we want to understand that energy, our investigation has to start where all the action is, inside the unbelievably dense, tiny core of the atom. We're going inside the nucleus.
Now, inside the nucleus, we've got 2 key players. First, you have the protons, which are positively charged. They're the ones that determine an element's identity. You can think of it as their atomic ID card. Then you have the neutrons, which are, neutral. At first glance, these neutrons might just seem like packing material, but trust me, their role is absolutely critical.
So physicists have a really simple shorthand to describe any nucleus, which is pretty handy. Let's take carbon-12 as our example. You see the C? That's just the symbol for carbon. Easy enough. The number on the bottom left, the 6, that's the atomic number. That tells you how many protons it has. And the number on the top left, the 12, is the mass number. That's the total count of protons plus neutrons. So with just those 3 little things, you know the exact recipe for that nucleus.
Okay, so what if you mess with that recipe a bit? What happens if you add a couple more neutrons? Well, the number of protons doesn't change, so the atomic number, that 6, stays the same. It's still carbon. But the mass number up top gets bigger, and that's what we call an isotope. A perfect example is carbon-14. It's got the same 6 protons, but it has 8 neutrons instead of 6.
All right, now that we've got the basics down, we have arrived at our first big mystery. I like to call it the case of the missing mass. And it all starts with a really simple accounting question. What happens when you weigh the individual parts of an atom and then weigh the whole thing all put together?
So let's try to build a helium nucleus from scratch. We'll start with our building blocks, 2 separate protons and 2 separate neutrons. Now, if you add up their individual masses and we measure these in something called atomic mass units, or U for short, you get this number right here. Got it? Just keep that number in your head for a second.
Okay, but here's where it gets weird. If you go out and measure the mass of an actual fully formed helium nucleus, one that's already assembled, you get a slightly smaller number. Yeah, you heard that right. The whole thing is somehow less than the sum of its parts.
So there's a definite discrepancy here. It's a tiny fraction of mass, sure, but it has seemingly vanished into thin air. So where did it go? And this isn't some measurement error, believe me. This is a fundamental clue. And it points us right back to our old friend, Einstein.
And here it is, the solution to our little mystery. That missing mass, it didn't just disappear. It was converted into the very energy that now holds that nucleus together. We call this binding energy. It's a perfect, real-world, honest-to-goodness demonstration of E equals mc squared in action.
But solving one mystery in science often just reveals another, sometimes even bigger one. It's like peeling an onion. So if the nucleus is held together by this binding energy, how in the world does it overcome the immense repulsive force that's trying to tear it apart from the inside? I mean, really think about this for a second. Protons are all positively charged, and one of the first things you learn in physics is that like charges repel each other. They push each other away. So a nucleus should be like stuffing a bunch of people who hate each other into a tiny phone booth. It ought to just fly apart instantly.
The answer is another one of nature's fundamental forces. It's called, appropriately enough, the strong nuclear force. And you can think of it as cosmic superglue. You've got the electromagnetic force, which we're all familiar with, pushing those protons apart over long distances. But the strong force is ridiculously powerful, way more powerful, but it only works over incredibly short distances. Inside the tiny confines of the nucleus, it's more than strong enough to completely overpower that repulsion and hold the whole thing together.
And this is where the neutrons come back into play. It finally explains their role. See, they feel that attractive strong force. They contribute to the glue. But since they have no charge, they don't add any more of that repulsive electrical force. They're like neutral mediators, adding stability. This is exactly why bigger nuclei, the ones packed with lots of protons, need even more neutrons to keep things from flying apart.
So what you have in the nucleus is this incredibly delicate balancing act, right? A cosmic tug of war between the repulsive electric force and the attractive strong force. But what happens when that balance is just a little bit off? Well, the nucleus becomes unstable, and when something's unstable, it has to find a way to fix itself.
In this self-correction process is exactly what we call radioactivity. The unstable nucleus is just trying to get to a more stable, lower energy state. And the way it does that is by kicking something out, either energetic particles or just pure rays of energy. It's nature's way of rebalancing the atomic books. Now, this radioactive decay comes in three main flavors. First up, you've got alpha decay. This is when a heavy nucleus just spits out a chunk containing 2 protons and 2 neutrons, which is basically a helium nucleus. Then there's beta decay. This one's really cool. A neutron actually transforms into a proton and shoots out an electron. This whole switcheroo is managed by another fundamental force, the weak nuclear force. And finally, you have gamma decay, which is the simplest. It's just an overexcited nucleus calming down by releasing a blast of pure energy, a gamma ray.
Now, if you look at the results of this, you see something pretty amazing. In both alpha and beta decay, the number of protons changes. And what did we say determines the element? The protons. So the element itself actually transforms into a different element. It's like real-life alchemy. And just look at the difference in penetrating power here. An alpha particle is stopped by a single sheet of paper. But a gamma ray? You're going to need a thick slab of lead or concrete to stop that.
And this brings us right back, full circle, to that case of the missing mass. Remember how mass was converted into binding energy to form the nucleus? Well, the exact same thing happens in reverse when it decays. The total mass of the pieces after the decay is less than the mass of the original nucleus. That missing mass has been converted into pure kinetic energy. That's the energy of the particles flying off at high speed. And that, right there, is the fundamental source of nuclear power.
So when you really get down to it, E equals mc squared isn't just some abstract formula on a blackboard. It's more like a page from the universe's own operating manual. It explains why some atoms hold together and why others fall apart. And in doing so, it reveals this absolutely immense reservoir of energy hidden inside the nucleus of every single atom that makes up you, me, and everything around us. It's a powerful reminder that sometimes, inside the tiniest, simplest looking things, lies the power to change the entire world.